So to start us off, we have Praharsh, who's gonna talk about CAD-based shape optimization of a pin-pin heatsink using the CHT solver in SU2.
Hello everyone, it is my pleasure to present to you our work on CAD-based shape optimization for heat transfer applications. And this work is part of my PhD done in collaboration with Vito and TUDelf for the group of Propulsion Power and Thermal Energy Systems group. Before we begin, let me invite you to imagine that we are in the year 2040 and you are planning your travel to SU2 Conference, probably in Varena here in Villa Montestero. You would be planning your travel and thinking of probably electric aircrafts or more hybrid aircrafts and some sustainable options. But for that to be a reality, thermal management is extremely crucial. And for that, we need more innovative designs of heat sinks. One way to push the limits of heat sinks is to use shape optimization, and this is possible using SU2. So this will help us improve the performance, so in extracting maximum heat transfer while minimizing operational losses. And this is conventionally done with FFD boxes or free-form deformation boxes in SU2. But one limitation of that is that we have limited control over our design surface, and that doesn't allow us to impose geometric constraints very well. So one solution for that is to use CAD-based parameterization, where we have complete control over the design surface, and that allows us to impose geometric constraint effectively. So combining shape optimization with CAD-based parameterization is very promising, but is currently unexplored. So that has been my main focus in my PhD, which is to develop an optimization framework which couples adjoint-based shape optimization in SU2 with CAD-based parameterization. And for that, I'm using the latest version and the master branch for conjugate heat transfer simulation in SU2 along with the adjoint computations. And for CAD parameterization, I'm using Parablade, which is initially developed for turbo machinery blades, but then with the recent extensions, it has been extended for applications in heat transfer. So just to give a bit of context over the CAD parameterization, we can define the NURB surfaces using a camber line and a thickness distribution around the camber line, and stacking the profiles of the blades together, we get a 3D profile. So this is how we do the CAD parameterization in turbo machinery. And likewise, to extend it for more aerodynamic heat transfer design, say for circular pins or more novel design, we can use the same approach. So this is our general CAD parameterization framework. Next, you would wonder, how do we compute the sensitivity? So a part of it comes from the SU2 computation, which was the flow sensitivity and the mesh sensitivity for a given set of design variables. And the rest, which is the CAD-based sensitivity, is achieved from the SU2, from the Parablade solver. But more crucially, it is important to know what is the sensitivity computation for conjugate heat transfer problems. And for that, I would refer to the work by Ole and the group at Professor Gauker's group, where they have clearly established how the cross-dependent terms in multiphysics are used. And to extend that with CAD-based parameterization, one simple way was to know that there is a contribution for the sensitivity from the flow solver and there is a part of the contribution from the heat equation solver. And one simple way is to have the interface modeled using the same parameterization for the fluid and the solid, and the sensitivity would be the sum of the two. So this would help us achieve the overall conjugate heat transfer sensitivities. So with that, now let's move on to the preliminary results that I obtained using the CAD-based sensitivity and the computation. For that, I focused on the 2D conjugate heat transfer case, which is available online for static conjugate heat transfer solver. And it is a steady laminar incompressible case with a Reynolds number of 40. And we have the internal solid core heated at a higher temperature compared to the overall flow. And we want to observe the flow and heat transfer in this case. But before moving on to the optimization, it is crucial to check if the gradients that we obtain from our design framework match well, and if they are accurate enough to proceed with the optimization. And one way to do that is to compare the gradients obtained with the adjoint method with the gradients obtained with finite difference. And we did that for our main objective functions, which is drag and the total heat flux. And we achieved a satisfactory match for our design variables for a preliminary case. And using this, we move on to the 2D shape optimization results for the same case, where we have the flow across the laminar flow across the heated cylinder. But in this case, we want to minimize drag by heat transfer, where the objective is normalized, and we are constraining the area. So this is something similar to the case of Tom Economon, where he published for a single zone case. But now this result is for the available multi-zone case, but with conjugate heat transfer. And this is the kind of results that we obtained for this case, where we see the evolution of the objective function plotted with design iterations, and we see a performance improvement of 3.19%. And this is the kind of shape which actually is similar to one of the shapes that we got, but this is for the multi-zone case. And we get performance improvement of drag and heat transfer coefficient together. And this is the comparison of the optimum shape with the baseline. So with these preliminary 2D results, then I moved on to the 3D optimization case, where I started with an exemplary pin-fin heat sink, where the flow could be modeled using steady state incompressible flow with conjugate heat transfer and having uniform heat flux at the bottom. But before moving to the fully turbulent case, currently what I have is the a laminar case with 4 inline pin fins, which is also simulated with using a rather coarse mesh. So for this case, our main objective is to minimize the pressure drop across these pins while maximizing the heat transfer. So a normalized objective function would be this, where we are constraining the volume so that it does not become excessively large, and also bounding the design variables. And this is the kind of result that we get. We can see the evolution of the objective function with the design iterations, where we get a performance improvement of 37.4% in a simple case. And this is the kind of shape that we get, where you could see it's enlarging sort of the bottom where we have larger heat flux, and minimizing the central core area where there is larger drag or larger pressure drop. So with this, I also tried several other explorations where I want to reduce the complexity, in the sense that probably this volume constraint in this case is not needed, and then what kind of results do we get. And you can see the results for a different case, where we get a larger performance improvement for pressure drop while also getting a higher performance improvement for heat transfer rate as well. Likewise, I did it for a different objective function where we are just maximizing the heat transfer while constraining the volume and then also allowing for a larger bound of design variables. And this is the kind of shapes and the performance improvement that we get. However, the whole optimization chain or optimization problem in this case did not converge completely. So I'm still facing a lot of challenges. And the main challenges are linked with mesh deformation and the subsequent mesh quality. Another challenge which we have is the geometric constraint and the bounds, especially for the intermediate iterations. So while these are the cases which converge, there are some cases where it could have gone further and achieved further design. So my main focus for the next phases would be for this, and I would really appreciate if there are any suggestions or discussions later on. So overall, in this work, I extended the CAD-based shape optimization to handle multi-physics problems with multiple design surfaces. Along with that, we achieved promising results with the conjugate heat transfer solver for the 3D exemplary pin fin. And my next focus will be on enhancing the robustness of the optimization. And that would be in terms of mesh deformation and probably regeneration and setting up appropriate geometric constraints. So with that, I would like to thank you for your attention and I invite questions and suggestions.
Questions? Was a photo finished there, but Naiso, you want to go first?
Yeah, I think two questions. So, the first question is how flexible is the CAD-based part? So, is it dedicated to a specific program or easy to extend other CAD programs? And second is, can we all already download and use it, or will there be a week or so before?
Yes, thank you for the questions, thanks. So,
Can you just
okay.
summarize for the...
So the question was, how flexible is the CAD-based framework currently? And if the second question was, if you can already download and use it. So for the first question, yes, we did demonstrate that apart from just the turbo machinery blades, you can also use it for different shapes of pins and tubes. But then one constraint is that in the current framework, we still are satisfying G2 continuity. So these are all smooth surfaces. For example, if you want to do it for offset strip fin, which may not be smooth in the current, say it might not have G2 continuity, then we might need some modifications. But then for most wide range of G2 continuity shapes, it is possible to parameterize and use it for optimization. Regarding the second problem, we have the available code, which is currently available through Nitish's GitHub currently. But then the further extensions are still internal, but once they are refined and worked upon further, we would be discussing on how to release them soon.
Toby, you have a question?
First question is regarding boundary conditions. It looked like the kids, they are all set. They are set that no, they are not connected by our basic, right? So the boundary condition is probably set either a heat flux or probably those heat flux, right? That we put into the pin bottom.
Yeah, so indeed. So in this case, the boundary condition is that we have heat flux on the bottom surface and also for the solid surface of the pin at the bottom. But then the pins are not connected. So what you said is absolutely right. So it's the heat flux and the pins are separate from one another.
And in terms, because you're using already, you have CAD representation. I think what you can do in terms of mesh, such as have remeshing or meshing workflow that just accept a set file, and then you can, once you have a new CAD, you can run through the green or workflow, and maybe that's creates a mesh, because I suspect you're just using the SU2
SU2 def, yes, correct.
Also your, which,
Correct, indeed, that's right. So one suggestion is the suggestion from Toby is to use the step file which we can extract from the CAD parameterization. And then, as you rightly said, currently I'm using only the deformation settings, the elasticity model available in SU2. And then as we have large deformations, the topology is still maintained, but then that leads to poor mesh quality. So indeed, that's one of my next steps to how to have regeneration smartly integrated. And I think the CAD parameterization will help in exporting the design and doing the remeshing.
I know that some people extract it from Mesh, SEL or have it super complete, and now you have it in-house.
Indeed, yeah, that's indeed a good advantage of CAD-based parameterization as well. Yeah.
So can you just say a little more about alpha? So what are your, how do you actually design the parameters for?
Yeah, so in this case, my alphas were actually the thickness variables along the camber line. So in 2D as well as 3D. So we have the circular representation using a camber line and thickness distribution, and those thickness variables were allowed to vary, and not just in one plane but also along the 3D profile as well.
Question over there?
I have two short questions. First, how many parameters do you have? And second question, are there unstable items you apply in this space and you don't enjoy how to
Okay, yes, thank you for the question. Regarding the first question, for each of the pin, we have uh, about less than 80 parameters in the current case in terms of thickness variable. So that into 4, so it's a large design space for a 3D case. And regarding the variation, in this case we are binding that, but then in the actual final case I think it would need a more smarter way of constraining the design variables, but it can have a larger variations as well. I don't know if that answered the second question. Yeah, so actually in one of adjoint doesn't work, as in the problem that I face is the flow equation diverges, and then of course then I couldn't go for the adjoint. But as of now, maybe I think there will be some case where I have the flow equations converge, but then adjoint equations diverging because of the poor mesh quality or say large deformation. But those are the main limitations in terms of mesh quality actually.
Thank you, Praharsh. Let's thank the speaker once again.